What's happening in recent years is we are seeing these applications in which time plays a very important role. Now, time has always been important in computing, just to orchestrate different parts of a computer. But what's happening is we are seeing applications where we are controlling the physical world, we are sensing the physical world, and that requires that the computation's notion of time and the physical world's notion of time be aligned. So the goal of Roseline is to really help applications cope with the uncertainty in timing that is occurring in these computing systems. So our project involves 5 different universities engaged in this. UCLA is the lead institution, but we also have CMU, University of California, San Diego, University of California, Santa Barbara, and University of Utah. Now, they all bring complementary expertise. So just to give you an example, UCSB, Santa Barbara, they bring expertise in formal methods to reason about how quality of time impacts the performance of control applications, which are an extremely important class of timing-aware applications. So Professor Joao Hispana is leading that effort. UC San Diego brings expertise in programming languages and how can timing and support for quality of time can be provided at the programming language level so that applications can make use of them. So Professor Rajesh Gupta's team there is doing that. CMU, one notch lower in the programming abstraction, operating system level support and processor architecture level support for providing quality of time. University of Utah provides expertise in protocols by which clocks at different nodes are organized, as well as some of the hardware expertise. And finally, we at UCLA are looking through the entire system stack, the necessary APIs and all, as well as new kind of clocks that help drive this timing stack.
One of the goals of Roseline is to create an end-to-end Linux stack that enables quality of time in applications. So our stack is comprised of 3 different components. The very first component provides basically an interface to applications through which they can bind to a common set of time, which they call a timeline. The second component is a scheduler, which exposes different virtual clocks for each of these timelines. And the last component is our system service, which synchronizes different virtual clocks in an adaptive and resource-aware fashion.
The rotary inverted pendulum is a pretty simple mechanical device that control designers can use to test their control algorithms. So it's got an encoder that can measure the pendulum angle, and another encoder that can measure the arm angle, and a motor, of course, that can drive the arm to try to make the pendulum upright. So the inverted pendulum is sort of this canonical example of a control system, and it makes the assumption, like many control systems, that the sampling and the actuation are synchronized, that they happen at the same instant of time. But when a controller is distributed across multiple devices, that assumption no longer holds. There are network delays that kind of wreak havoc on a controller. So the quality of time stack allows us to have both devices synchronized to a single timeline so that this assumption that the sensing and actuation happen at the same time is held.
One way to control the quality of time is to switch between different local oscillators. This switching demands oscillators that are very quick at the startup. We were able to develop a method by initially energizing the crystal device by means of a local oscillator. And by using this method, we were able to reduce the startup time by 100 times.
A traditional OS scheduler multiplexes the CPU so that multiple processes can run on the system. A real-time operating systems scheduler does the same task, except now all the processes have strict deadlines and periods that they must be run, and the real-time scheduler ensures that that happens. Quality of time is important to the real-time scheduler because it ensures that these deadlines are met across multiple devices.
Go is a suitable language for us because it has Go routine, which is in user space instead of thread in kernel space. So it's easier to modify the scheduler and build powerful things on top of it. It enables the notion of quality of time in Go. So the current version of real-time Go, we are able to do real-time scheduling, quality of time, and also parallel programming.
So what we are doing in Roseline is we are using this connection that we have with the physical world as a way to attract younger students. We run a program called Los Angeles Computing Circle, which seeks to go beyond the kind of computing that students get exposed at high school level out here. And we kind of try to expose them to the challenges that computing faces at the level of advanced technology, at the level of research. So for example, we have them explore how robots work and what's the control software of a robot looks like, or we expose them how you can create software which is able to maintain low power and high performance. Now that's the education component. Obviously outreach also goes beyond education. It's also about engaging with the industry, engaging with the broader community of researchers, and Roseline is also doing that, for example, by participating in the TAX effort, which is a timing aware application, or particular working group there focused on a new kind of APIs for timing applications. So in Haiti, post the earthquake, the infrastructure had become largely non-existent, and Anthony's team went there and established a power grid there for the villages and all. And part of the issue out there was also being able to monitor the state of this grid. Now, historically, this is done using these sensing devices called PMUs, which is how commercial grids operate, but these are very expensive. So what Anthony has done is created sensing infrastructure for that power grid that he has created using very low-end devices. Now maintaining their timing across wireless networks which were never designed for these kind of precise timing is a challenge, and that's what his group has been doing. So there are so many applications, so many exciting applications now that fundamentally depend upon a robust understanding of time. Just to take an example, drones or swarms of drones, the coordination among them depends upon time. The control of an individual drone depends upon time. So ways by which very resource constrained, potentially very tiny devices can have a good quality of time, not just individually, but across an entire network. So Roseline Technologies, we are already in collaboration with other institutions in the team. We are developing very resource constrained small drone systems which can precisely localize themselves by making use of very precise knowledge of time. So by providing this sophisticated stack within the system which mediates between the providers of time, the clocks, the GPS, and the users, namely the application, it helps create systems that are more robust as well as more secure.